So welcome to this seminar with Srikanth Srinivasan, who's going to tell us about lower bounds for algebraic formulas.
Yes, thank you.
Please.
Thanks very much. Okay, so usually in the beginning of every talk, I say ask as many questions as you want. But now I don't know if anybody will hear anything. So, but still ask as many questions as you want, right? Yeah. So I'm going to talk about this, and the reason for picking this topic is that it's kind of a very simple and clean problem, and it's a very simple and, in my opinion, clean proof. So I hope that you take something away from this talk. It's supposed to be fairly kind of a gentle introduction to the area. Yeah, so let's see how it goes. Okay, so what's the setup, right? So good. So the basic problem is the following. So it's a very neat kind of combinatorial / algebraic problem. And it just takes a slide to describe. So basic setup is we have this thing, a polynomial, right? So it's a polynomial in n variables of degree d. And given any such polynomial, right? So what's a polynomial? It's like an algebraic expression. So you can write it out as an algebraic expression, right? So here's a polynomial. So I have n variables, x1 through xn, and I'm looking at the sum of all pairs, sum of all products of distinct pairs of variables. Yeah. And I can have multiple expressions for the same polynomial, right? I can write it like the expression on the left, or I can use some kind of simple algebraic identities. I can say if I sum all the variables and I square them, that essentially gives me the polynomial I want, except for the square terms. So I subtract off the square terms, divide by 2. That's polynomial. So two different algebraic expressions, the same polynomial, right? And okay, all right, good. And the question we want to ask is, what's the smallest expression for everyone? Okay, so you have some polynomial you care about. What's the smallest expression? So for instance, the expression on the left here has size quadratic in n, right? Because I sum over all pairs of terms, I get a quadratic, an expression of quadratic size. Whereas if you look at the expression on the right, it's sort of linear size, because I sum n variables, that's linear size. I take two of these expressions, I multiply them together, that's just linear. And then I subtract off the squares, that's a linear number of squares. That's it. So it's a linear size.
So the degree of x squared times y, is it 2 or 3?
The degree of so do you see an x squared times y here? So
No.
Oh yes,
I'm just asking.
That's right.
Is it the max exponent or is it the sum of exponents?
That's right. It's the sum of the exponents.
Sum of exponents.
It's the sum of the exponents. Yeah. So a degree of x squared times y would be 3. That's right.
Yes. Okay.
That's it. Yeah. So right. So you have a polynomial of some degree, and you want to kind of write it down as an algebraic expression. Right. You're allowed to use sums and products in this expression. You can nest sums and products together. You can come up with more complicated expressions. And the question is, okay, what's the smallest expression you can come up with? Right. Okay. So that's the basic set. Okay. Does this make sense? Is the question? Right. So that's the thing. And so that's it. So now the basic problem that we're trying to solve from a complexity theoretic point of view is again very simple. Find a polynomial, any polynomial you want. Yeah, find a polynomial. This polynomial shouldn't have humongous degree. Okay, so you can cheat in this question by coming up with humongous degree polynomials, but find a polynomial with small degree that has no such algebraic expression of small size. Okay, and small size here means polynomial in the number of variables. All right, so find any polynomial, right? Tell me the name of a polynomial, describe a polynomial to me that has no small form. Yeah, so that's the name of the game. And so it's kind of easy to make a few observations once you understand this question a little bit. Is that the hard part is not to show that there exists such a polynomial. Okay, so you can always sort of choose a polynomial at random in some way. And any reasonable way of defining what a random polynomial is has the property that a random polynomial does not have small polynomials. Okay, so a generic polynomial, a generic object satisfies this property. And the question is whether you can make this statement explicit, right? So I know that there exist polynomials that satisfy this property. And now can you tell me a polynomial which has this? Okay, make it think. So this is sort of all kind of very standard issue stuff in complexity theory. It's always the case. You know that certain things exist. Can you make them explicit? Okay, and this is the same thing in a certain situation. So now, not that you need to care about it. I feel like the question is kind of very combinatorial and interesting by itself. But if you really care about what the connection to this, connection of this question and standard complexity theory is, it's the algebraic version of lower bounds for a complexity class called NC1. Okay, so this is kind of a well-known complexity class. And we want to do lower bounds for this class, and this is sort of the algebraic version. That's a connection complexity.
Can I ask a quick question?
Yes.
So How do, like, so I guess it's by some counting argument.
Yeah, that's right.
A random piece satisfies this property. How do counting arguments work in this setting? Because you have kind of coefficients if you have an infinite field.
Right. If you have an infinite field, counting arguments work in the sense that you don't count the number of polynomials, but they sort of, you can count the dimension of such polynomials. Sort of, it's like a dimension argument.
Okay.
Yeah. But you can do something very analogous to count. Okay. All right. So that's the setup. And so now this is the question, right? So you want to find polynomials that have no small formulas. So now with this kind of complexity theoretic insight that it's connected to NC1, etc., we can actually formulate reasonable candidates for such polynomials. Okay. And one such reasonable candidate, you can see what I'm doing, is sort of the star of the show in the talk that we're going to be, in the result that we're going to be seeing. Okay. Yeah. So good. So this is called the iterated matrix multiplication. Okay. So so this is a very simple polynomial, and this is what we're going to be studying. So basic setup is the following. The underlying variables of the polynomial. Oh, see, this is happening a little too often, isn't it? Okay, well. So so the underlying variable set of the polynomial, right, is a set of D matrices. Okay, so the right-hand side here, there's a set of D matrices, each of them is n by n. That's the underlying variable set of the polynomial. Okay, and so you should think of each entry of each of these matrices as a new variable, fresh variable. Yeah, and so now you multiply these matrices together, right? You multiply them together. You're going to get a matrix, that's a matrix on the left, I'll call that X. Okay. Now every entry of X is a polynomial in the entries of these matrices. Okay. And it doesn't matter which entry I look at. Usually we look at the top left entry, but you could look at any one of them. And you can take any one of those polynomials. And that's called the iterated matrix multiplication. Okay. So IMN. Yeah. And so this is sort of a candidate hard instance. We suspect that this polynomial has no small algebraic forms. Okay. And the reason we suspect it is that this is an algebraic version of something that's of the graph reachability problem. Okay, so you have a graph, right? And you want to check if one vertex is reachable from another. The standard way of doing it is to take the adjacency matrix of the graph and power it, right? And this sort of corresponds to that. You're multiplying a bunch of matrices together, it sort of corresponds to that. So it's sort of the algebraic version of graph. So we expect that this polynomial has no small. Okay, and now one of the big questions in the area is to prove this for this polynomial or for any other, but this one's a particularly interesting. Okay. All right. So before I go ahead and kind of tell you a little bit about our results, let me start off by saying what is known about formula construction for this polynomial. Okay, so the basic setup is this is the polynomial you're interested in. What's the smallest algebraic expression I can come up with this polynomial? So how would we go about coming up with expressions? Well, you just look at the polynomial that we have, right? So it's a product of a bunch of matrices. So it has this very nice recursive structure, right? You're just multiplying a bunch of matrices together. So if you wanted to construct algebraic expressions for this polynomial, one thing you could try is kind of use a very simple divide and conquer strategy. Oh, I see. That's good. Yeah, use a very simple divide and conquer strategy. So what will the divide and conquer strategy be? You have a bunch of D matrices that you multiply. So you just break the group of D matrices into, wow, okay, so this is getting like, should we try to, yeah, maybe. Move it a little bit. Maybe the wire is bending a little too much.
Is it the same problem on the screen?
No.
There's no problem on the screen.
So we have no problem. What happened now?
Where you want to stand by? It's not. I do not touch them.
Which one was it that we were?
It's perhaps the seem to come up almost immediately.
That's great in running, isn't it?
No.
How many complexities does it?
This is exactly what and also how much time, right? We were doing it half an hour before the talk began.
This is the lower bound
Yeah.
too, so
Right.
this is.
But which,
It's not the first one?
I tried it already.
Okay.
What's going on now?
So now we're just
We're having a problem with projecting to that screen, right?
This one.
So somehow we've had problems in 116 last time also. I don't know what the issue is. Okay, going back to number 1. I don't know if these are somehow Macs don't play well with this environment.
yes, I think this is it.
This is it, is it?
Yes.
Okay, but I mean, you have your slides there. We have the slides there. Just keep going.
All right. Okay.
So, like, people on Zoom can see. Yeah, but I don't think.
Okay. Okay. All right. So we've introduced the basic problem. So the question is to prove lower bounds for algebraic formulas.
Yeah.
And now this is a polynomial that we believe is high. So let's try to first come up with some sort of idea of the construction, right? And then that kind of gives us something to shoot for. So this polynomial, you're just multiplying the n by n matrices together. So very natural strategy for constructing a formula for this polynomial is to kind of use a divide and conquer strategy. So you have d n by n matrices. So break it up into 2 blocks of d by 2, right? So imagine that I multiply the first d by 2 matrices together and the last d by 2 matrices together. So I'll have 2 matrices A and B. And the polynomial that I care about now, let's say it's the top left entry. So it's sort of just the dot product of the first row of this matrix and the first column of this matrix, right? So that's what I want to do. And this gives me a recursive strategy, because what I want to do is I want to compute each of these little boxes over here, each of these little boxes over here. And that's sort of the same polynomial, but with degree d by 2 instead of degree d. So I do this, and that gives me a recursive strategy. Okay. So they tell me that the polynomial I care about is a sum of a bunch of copies of products of pairs of polynomials. Yeah, does that make sense? Yeah. Recursive strategy. And now if you kind of work out, so now you recursively write down formulas for these. And if you kind of work out the parameters of the recursion, you get a formula of size n to the log times the log of the number of variables. I'm sorry, number of matrices. Okay, so you have d matrices, so it's n to the log. Yeah. So this kind of very basic divide and conquer strategy is all we've known for this. Yeah, and we've known this in some form or the other since the 60s. Okay. So it's a very reasonable conjecture, in my opinion, to make that this is static. This is the best you can. You cannot really improve on this by a whole lot. Okay. And that's sort of our goal. We want to show that this is static. Okay, so we're multiplying d n by n matrices together, the best you can do is enter the log. If this were not true, then some very interesting things would happen in complexity theory. And the basic thumb rule is that nothing interesting is ever going to happen in complexity theory. So that's the setup. All right. And the main result that we prove is some sort of lower bound. Okay. So this lower bound that I'm going to prove, that I'm going to tell you about, is sort of not the ideal lower bound that we'd like to prove. In 2 senses, it's a lower bound for a special kind of formula. Okay, so these formulas are what are called set-multilinear. So let me just tell you quickly what they are. So here's the polynomial we care about, the IMM polynomial. So if you expand out the definition of the polynomial, right, you don't have to understand the details of this. But the main thing you need to understand is that every monomial in this expression sort of multiplies one variable from each of these matrices, right? If you're going to multiply them together, then you have to take one variable from here, one variable from here, one variable. Okay. And a polynomial that has this feature is what I call a set-multilinear polynomial. Okay, so that's a polynomial which has sort of, here every monomial has exactly one variable per matrix. So in general, if you can take the variable set of the polynomial and partition it into a number of parts, so that every monomial contains exactly one variable per part, so that's a set-multilinear. Yes, that's a definition. And now when you have a set-multilinear polynomial, it's sort of very natural to look at what are called set-multilinear formulas. Okay. So intuitively, a set-multilinear polynomial, it sort of doesn't make sense to multiply 2 variables from this matrix here, right? Because this never occurs in the final polynomial. Yeah, and so it doesn't make sense to do things of this form. So set-multilinear formula is essentially an expression, it's just an algebraic expression, where you don't do any of these things that don't make sense. Okay, so you never multiply 2 variables from the same matrix. You never do some weird stuff like computing high-degree polynomials and then canceling them out and doing something weird. So essentially, any sub-expression of this formula itself is a set-multilinear polynomial. Okay, maybe in a subset of these matrices, maybe not in all of the matrices together, but it's some subset of the matrices. So such a formula is what is called a set-multilinear. Okay, does this make sense at a high level? Right, so it's a very restricted kind of formula because you're not allowing certain computations to occur, but it's kind of very natural in the context of polynomial that we're dealing with. Yeah, and as we'll see, it's actually intimately related to proving general formula. Okay. All right. Yeah. So here's the main theorem. Okay. So what we prove is a super polynomial lower bound on the size of any set multilinear formula computing this polynomial. Okay, so you're multiplying n by n matrices, so the two parameters are now the same. And in this context, we expect that the right upper bound is n to the log n. That's sort of the thing that we expect. So we prove a lower bound that's not quite as strong as that. Okay, it's like n to the log n. So it's a super polynomial in n, but not quite the right super polynomial.
Is it important here that both are the same, or would this be just n to the log t?
Right. So it would be d to the log n. You write it in terms of both n and d together. Right.
Okay.
So yeah, for small values of d, it wouldn't really give you anything interesting. But when d equals n, it gives you. Okay. So that's it. So that's the main statement of the theorem. So any kind of questions about this? Okay. Okay. Yes.
But we could imagine that there were some formulas that were not in this form, right? That didn't work.
That's absolutely right. So we don't know that. So in general, we don't know any lower bounds for arbitrary formulas without any restrictions. Okay, so that's a great question. This is a great candidate, right? But this is the first set multilinear formula lower bound candidate. And I'll tell you in a little bit why this is interesting from the point of view of doing general formula. Okay. All right.
But you're making the argument that somehow intuitively, like you don't see any way of violating set multilinearity that somehow would buy you anything.
That's right.
It's not like monotone circuit lower bounds where monotonicity is like clearly a restriction.
That's right.
Like anything you could think of would automatically satisfy this.
This
At
is
least as of today.
As of today, yeah. So there are some very fine grained separations. There are slight things that you can buy without set multilinearity. So losing set multilinearity does gain you certain things, but not enough that I expect this upper bound to be improved. So maybe you could improve the exponent here, the constant in front of the exponent, maybe by a factor of 2 or so. So that's what I know that non-set multilinearity buys. Okay. All right, so that's the main statement of the theorem. So you can see that it's kind of off from what we'd like to prove in 2 ways. It proves lower bounds only for certain kinds of formulas, and it proves only a super polynomial lower bound, but not the right super polynomial. Okay. And so let me tell you a little bit about the previous results. As I said, nothing is known for general formulas, but something was known already for set multilinear formulas. And put my results, the results we have in the context of these old results, and tell you why this is interesting. Okay. So let me just go through this short list of previous results. So as we saw already, there's this divide and conquer upper bound, very simple construction, which is of size n to the log t. And if you stare at this construction, right, we're not doing anything unexpected. We're never multiplying two variables in the same matrix, for instance. Okay, so this construction is very much set multilinear. So this is a set multilinear upper bound of from n to the log t. Okay. And back in the 90s, the first people to sort of study this question of proving lower bounds were Nisan and Wigderson. So it is a very influential paper from back then, where they showed that this construction is more or less tight, okay, when n equals 2. For set multilinear formulas, I should say again, when n equals 2. So you're just multiplying 2 by 2, those small matrices, okay. So you can look at that expression up there, right? So when you're multiplying 2 by 2 matrices, then the right upper bound is 2 to the log t, which is like polynomial in D, okay. So that's kind of a trivial lower bound. So you can always prove a polynomial lower bound. So it's not really a very interesting lower bound. So the results were actually only interesting in some, if you put further restrictions on the kinds of formulas you consider. Okay, so you need some restrictions on what is called the depth of the formula. So the amount to which you can nest expressions within one another. All right. So we're not going to look at this. We're going to look at general formulas. And in this context, the first such results were proved by another paper of Raz, where he looked at a slightly different polynomial, not the iterated matrix multiplication polynomial, but something called the determinant polynomial. Right. So you've seen probably when you have an n by n matrix, you can talk about the determinant. And the determinant is a polynomial in the entries of the matrix. So you look at that polynomial. That's also a set multilinear polynomial. If you think of the sets as the rows of the matrix under consideration, right? So what Raz showed is that any set multilinear formula for the determinant must have this size, n to the log. Yeah. So it's very interesting, right? It's like n to the log n is the lower bound we want to prove, and he proves such a lower bound, but for a different polynomial, the determinant. Okay. He doesn't actually get it for iterated matrix multiplication. There's a very good reason for that. We'll get to that. And so the thing about Raz's result is that he gets a stronger lower bound, and he also gets it to hold in a slightly more general setting that we won't really talk about. It's called the multilinear setting. So that's a kind of a story for another day. All right. So these results were subsequently extended. So Raz has some more work. So you have other polynomials for which you can again prove this kind of quasi-polynomial bound. And in this context, what we do is again to prove a weaker lower bound than this one, right? For this problem. Okay, so this is kind of the main reason.
But if the lower bound for determinant, that's an example of something that you can do better if I give you a general.
That's exactly it.
Algebraic circuit.
That's right. So for the determinant, we expect that the set multilinear complexity is very different from general algebraic complexity, but this is not the case for iterated measures. Okay, but just to say that you have these lower bounds from before, and what we prove is now a super polynomial lower bound, but a weaker lower bound for a different polynomial. Okay, and this is kind of, I guess, not very inspiring in some sense, right? Because so in general, the story of complexity theory is that you want to prove stronger and stronger lower bounds. Right? Where you don't have anything, you want to prove a super linear lower bound. Where you have something, you want to prove a super polynomial lower bound. And where you have a super polynomial lower bound, you want to prove an exponential lower. Okay, and this is sort of the name of the game, and it makes sense from a certain point of view because stronger lower bounds lead to stronger things like pseudo-random generators and other things that you want to do. Okay, whereas what we are doing is kind of exploring a different trade-off in complexity, which is kind of interesting, and I thought you might want to know about. And here, what we are doing is sort of our aim is to prove not a stronger lower bound. So ideally, we'd like to start with Raz's lower bound and extend it to an exponential lower bound. That would be great. But instead, we're asking for something else, right? And what is it that we're asking for? We're asking for a weaker lower bound, but for a problem with more structure. Okay, so we're kind of trading off the strength of the lower bound for structure in the problem in which we prove the lower bound. Okay, and this is a kind of a different kind of trade-off. And this allows you to prove some other kinds of things, which are very interesting. Okay, and in particular, in this context, I want to say that this is progress towards removing this restriction of set multilinearity. Okay, this progress towards going general formula. Okay, and let me try to kind of explain that. All right, so why is it that we want to prove low bounds for this polynomial? Why is this an interesting problem? And why is it that Raz didn't do it already? Well, the reason is kind of that this problem has a very nice embedded recursive structure in it that you've seen already, right? So in particular, imagine that you had, you want to multiply n by n matrices, right? And imagine that now you look at the sub-problem of multiplying d n by n matrices. And think of d as much smaller than n, okay, maybe log n or so. Okay. So just for a second, imagine that we had a small expression for multiplying d of these. Okay. Then what you could do is use this expression recursively, just in the way we've seen, to multiply n by n matrices, right? Because you would kind of group them into bunches of n by d. Employ this expression, recursively apply the expression again and again and again.
I apologize for interruption. I think the remote control of the other screens here. I can see two things.
So did you guys would turn off our screen?
Yeah. But this is not for this one, right?
I think both operated that.
Oh,
one.
sorry. I acted for it.
That was another, sorry.
I'm assuming this thing of.
It takes half an hour to get it. Oh,
Okay, good. It's coming.
I don't think we'll let you have it.
Wait, just take the cookies too. I mean, it's.
All right, good. So I guess we have HDMI 1.
Yes. Was that what we had?
So,
Yes.
but if he uses it in another room and stops our.
I think you pointed in the
so-
other direction. It's fine.
Oh,
Shouldn't even go to the last one.
Yeah, my brain did not process that while talking. I just pressed it. To experiment on that.
So I don't.
okay,
remember.
So it works, right?
I think I'll be good.
The remote works, yes.
Yes.
Are we on HDMI 1?
Yes, we were.
You can look at the
Yeah, I
screen
think
and
it's
continue
going
telling us the story. If you can multiply D matrices together, right? Please tell me.
Yeah, let's see some. So,
Yeah, some
Okay.
activity.
Make sure you have it.
No, it's okay. Don't worry about it. I
Keep
mean,
this one outside the glass doors.
yeah.
And don't point in a loud direction.
I bet this doesn't happen at Aarhus.
I don't know, we can see the slides in the.
Yeah, that's why we're receiving them. So three matrices, come here, you'll see.
Okay.
I should have pulled my binoculars, I have to find.
I think, yeah, keep flowing and we'll try to solve it.
All right. Okay, great. So I'm going to try to make a rather subtle point, which would be even harder to see because you're looking at those slides. Let me see if I can try to tell you the story anyway. So
You'll see the slides.
You can see the slides.
Sounds good. So imagine, right? So you're trying to multiply n by n matrices, so lots of n.
Yeah.
So imagine that you had a kind of a sub-expression, kind of a small expression that could multiply d of them, small number of them. Now you could use this idea recursively to multiply n of them, right? You just kind of group things in blocks of size n by d, recursively use this expression you already have, and then use the expression you have to multiply the d.
Yeah.
Okay, so that's the basic setup. So now if you kind of think about this for a little bit, you see that if you have a really small expression for multiplying d n by n matrices, you also get a smallish expression for multiplying more n by n matrices, for instance. Okay, so this tells you kind of an interesting fact about this problem, which is that if you believe that the kind of the naive divide and conquer algorithm that you've seen, if you believe that that algorithm is tight, then it has to be tight not just for n matrices, it has to be tight at all smaller numbers of matrices. So if you believe that it cannot do it more efficiently at n by n matrices, then you cannot do it more efficiently for a smaller number of matrices.
Yeah.
Okay. And so this is kind of good news, which means that the harder cases of the problem intuitively are when d is small. Okay, that's kind of the harder case of the problem. Okay. So in this situation, when you have when you believe that this is the case, so in particular, it should be easier to prove lower bounds in the set multilinear case. So for the same reason, you also believe that the set multilinear case, the tight thing is the n to the log n thing, which means that again, using the same argument, it should be easier to show that for a small number of matrices, n to the log d is tight. And here's kind of the kicker, is that in the case when the degree is really small, right, like log n or something, so Raz has shown that a general formula complexity is sort of the same as the set multilinear. Okay, so if you prove the tight lower bound for set multilinear formulas, then you get the same kind of lower bound for general. Okay, and so what does this mean, right? This means that for proving general formula lower bound, it suffices to prove tight set multilinear formula lower bound for multiplying large numbers. Because if you have the tight lower bound there, then you get the tight lower bound for a small number of matrices in the set multilinear case. And what Raz has shown is that this corresponds to a tight lower bound for general formulas.
But do you need this omega of log n exponent for IMM and
Right. So, but in order to get this whole thing to work, what you need is the tight lower bound for set multilinear formulas for a large number of matrices.
Yeah.
Okay. So in some sense, we are making progress towards this question. If we had the tight lower bound for multiplying n of them, we get general formula without any sort of restriction. We're not able to do that yet, but what we are able to do is get the first super polynomial lower bound for multiplying lots of matrices. So this sort of makes progress in that direction, but unfortunately, we are not quite there. So this is the sense in which these lower bounds are qualitatively different from previous lower bounds. So they shouldn't be compared on a quantitative level. In the qualitative sense, it's really a kind of a different kind of stuff. Okay, so that's sort of the setup and why this thing is interesting. And so next thing I want to tell you about is sort of like a, oh wow, okay, great. Okay, fantastic. Yeah. Okay, so that's kind of the setup and the kind of results we have and why we start looking at that. So the next part of the talk that I wanted to do in the first half was to tell you a little bit about how one goes about proving these kinds of things. Okay, so I just want to kind of give you a flavor of the proofs. They are very simple combinatorial / algebraic arguments. Okay. But I think they're kind of worth knowing, and they're also useful in many other scenarios. So for instance, I'm proving some interesting combinatorial statements about graphs, these kinds of things come up. So they may be independent. Okay. So let me tell you a little bit about this, and the kind of the results, the techniques I'm going to talk about hark back to this paper of Nisan and Wigderson that we discussed briefly. And this method is called the partial derivative, and you'll see why it's called this. Okay, so let me start off with a baby version of the problem of proving these kinds of lower bounds. Okay, it's really kind of a very simple version, but I feel like the techniques become very clear in this setting. Okay, the basic setup is this. So I have two sets of n variables. Okay, so I have x1 to xn and y1 to yn. So two sets of n variables. And here's a very simple set multilinear polynomial. Right. So I just take these two variable sets and I take the dot product between them. Okay, there's a dot product between them, and that's a kind of a set multilinear polynomial. Okay. So this is clearly already a small expression, right? By definition, it's a small expression, But the question I'm going to ask is, can I compress this expression further? Can I come up with an even smaller expression for this in some sense? Okay. So what does that mean? So here's the kind of expression I'm going to look at. I'm going to say that try to construct a smaller expression for this, where each term of the expression, right, takes a linear polynomial in the x variables. So I can sum them together, x1 plus x2 plus x3 or something, times a linear polynomial in the y variable. Okay, so each term looks like this. And then you take a sum of a bunch of such terms. And then I want you to get me exactly this polynomial on the left. Okay, so this is kind of a set multilinear expression, right? We're never multiplying x variables together, we're never multiplying y variables together. So kind of a nice set multilinear expression. So what's called a sigma pi sigma formula. For the reason that you first sum the variables and then you multiply them together and then you sum things together again. So it's called sigma pi sigma. Okay. So now obviously you can do this where the number of terms is equal to n, right? Because that expression is already of this form, but you have n terms. And now the question is, can you reduce the number of summations? Can you reduce S to something smaller than it? Okay. Does that make sense, the question?
Yeah.
Okay, good. So if you stare at this question, you see that actually this is just matrix rank kind of hiding in disguise and so on. Okay. And so it's very natural to try to use some sort of linear algebraic techniques in order to answer. Okay. But let me kind of be a little bit verbose about it because it will help us in the coming slides. All right. So the basic setup, so I want to show indeed that you cannot do better than S equals n. And how would I show that? Well, what I'm going to do is I'm going to associate with these polynomials certain matrices. Okay. In general, given any polynomial, right, any polynomial set multilinear polynomial, I associate to it a matrix. Okay. And what are the entries of the matrix? They're just the coefficients. Right. So the rows sort of correspond to x1 to xn, the columns correspond to y1 to yn, the ijth entry is aj. Okay, so that's the matrix kind of polynomial. It's called a partial derivative matrix. Yeah, and you can see why, because this is kind of the partial derivative with respect to these two. That's why partial derivative matrix. Okay, so now let's look at this matrix for these polynomials in the consideration. All right. So for the polynomial on the left, things are really simple. So this is the partial derivative matrix again. The polynomial on the left, the matrix just has ones along the diagonal, right? Because you only have the xi, yi terms and zeros everywhere else. So you don't have anything else. So this matrix is just the identity matrix. Okay, so this matrix has rank n. It's a rank n. It's simple. And if you kind of, now it requires a little bit of algebra, but if you do it the right way, you can, it's very easy to show that each of these terms here, their partial derivative matrices have rank 1. They're rank 1 matrices. Okay, so each of these is a rank 1 matrix. And of course, the coefficients of these polynomials are going to add up to the coefficients of that polynomial over there. So the ranks of these matrices better add up, the sum of these matrices is going to add up to that matrix. So I need to add enough rank 1 matrices to get that rank n matrix. Right? And it's kind of a standard fact that when you add two matrices together, their ranks at most add up. They might not add up, but in the worst case, they add up. And that means that you need at least n terms of this form to add up to the polynomial. Okay. Yeah, does it make sense? So in this case, you really cannot compress the size of the sum to less than n. Okay, so it's kind of a very simple result. As I said, there's already a small expression, so it's not interesting as a lower bound statement, but already it tells you the kinds of techniques that are useful in proving statements. Okay, so let me push this a little bit further. So here I have just two sets of n variables each. To prove super polynomial lower bounds, I need to push this up to higher degrees. So now let's assume that instead of two sets of n variables, we have d sets of n variables. Okay, same setup, but we have a d set of n variables. And now we have some polynomial on the left there. I'm not going to tell you exactly what that polynomial is, but I want to say that it has no small expression of this form. Okay, so now again, each term in the expression is a product of linear polynomials in each of the underlying variable sets, right? So they're d variable sets. So I take a linear polynomial in each, multiply them all together, and sum a bunch of terms. Okay, again, this is called a sigma pi sigma set multilinear formula. Yeah. All right. So now, how am I going to do this? I want to use the same idea. Only when you take a polynomial of this form, it's not clear how to create a matrix out of it, right? I guess, yeah, I don't know. It's not immediately clear how to create a matrix out of it, but it's not hard. So what we do is that we take the variable sets of the polynomial. So now there are not two of them, but there are d of them. So we just divide them into two kinds. Okay. So I'll call them the row variable sets and the column variable sets. Okay. So I've given them different colors, but I'm colorblind, so I don't really know what the colors are. So I guess one of them is red and the other one is gray or something. It's red and gray, hopefully. Good. So you have two sets of, So you have two kinds of variable sets, right? The row variable sets and the column variable sets. Okay. And so what you're going to do is now, so this is going to define the matrix. So how? So take the polynomial. Again, it's a set multilinear polynomial. So every monomial is going to contain exactly one variable from each set. Okay. So it's going to contain a bunch of red, yeah, a bunch of red variables, one from each red variable set, and a bunch of gray variables, one from each column variable set. Okay. And now this kind of tells us how to form the matrix. So the matrix now, the rows are going to be labeled by all red monomials. Okay. And assuming that exactly half the variable sets are red variable sets, they're going to be n to the d by 2 of them. Yeah. And similarly, the columns are going to be labeled by the gray monomials. Yeah. And the entry corresponding to a red / gray monomial is the coefficient of their product in the polynomial vector. Okay. So it's kind of a direct generalization of what we did for two variables. Yeah. Does it make sense? So this is again the partial derivative matrix in this more general setup. Yeah. And now again, so we're going to set it up so that this polynomial, the one that we have up here, has for this polynomial, this matrix has large rank, ideally full rank, as big as it could be. So that would be n to the d by 2. So that's how we're going to set it up. And now we need to analyze the ranks of the matrices on the right. Okay. So let's take one of the terms in this expression. Yeah. So what's the rank of this thing going to be? Okay. So you can analyze this in all sorts of ways. But let me give you kind of one trick to analyze it, which will make life much simpler later on, which is kind of an observation. So I don't expect you to see this observation right away, but just take it on faith. That when I look at the partial derivative matrix of a polynomial like this, right? It's a product of polynomials in distinct variable sets. What happens is the partial derivative matrix of this is sort of the tensor product of the partial derivative matrices of each of these polynomials together. Okay, so if I look at the first polynomial, it's just in the variable set x1, so it has its own little partial derivative matrix. So it's just got a red variable set. So I define a partial derivative matrix for that. I come up with that matrix, and similarly for the second one, and third one, and so on. And I take the tensor product of all of these, and that's going to be the partial derivative matrix corresponding to a product. Okay, so if you don't remember what a tensor product is, it doesn't really matter for the talk much. So the only thing you're going to know is that the tensor product, the number of rows is the product of the number of rows in each of these matrices. The number of columns is the product of the number of columns, and the rank is the product of the ranks. Okay, so everything multiplies. Number of rows, number of columns, rank, everything multiplies. Okay. All right. So what's one of these matrices? Let's take the first matrix, for instance. What's the rank of this matrix? That's what you want to understand. Okay. So what is this matrix? So it only has row variables. Okay. So it has no column variables. So if I look at the partial derivative matrix of this, well, you're going to have a bunch of row variable rows, but there's no column variable sets. Okay, so the only monomial in the column variable sets is sort of the empty monomial, the empty string in these variables. Okay, so there's just one, so it's kind of just a column vector. Okay, and the column vector, of course, has rank at most 1. So this thing has rank at most 1, this thing has rank at most 1, and so on. So ranks multiply, and the rank of this whole thing is 1. Okay, so which means that so this is a sum of S, the S terms in this whole thing. There's a sum of S rank 1 matrices, and therefore the matrix, the partial derivative matrix corresponding to this expression has rank at most S. Okay, and now if we choose a polynomial judiciously, right? If we set it up so that this matrix is full rank, the only way you can manufacture a polynomial like this is to take S to be as big as the dimensions of this matrix. Right? So we should, if we set it up so the polynomial is full rank, we can get S to be as big as n to the d by 2. Okay, does that make sense? All right. So the last missing piece of the puzzle here is to come up with a polynomial for which this matrix actually has. Right. So what polynomial has this property? Well, obviously, right, we are trying to prove lower bounds for iterated matrix product. So it better be the case the iterated matrix product has this property. And indeed it does. So what you need to do is you need to choose your gray and red variable sets judiciously. Okay, if you choose them in a silly way, it doesn't happen. But if you choose them judiciously, well, it's not super clever, but what you do is you take the first variable set to be red, the second one to be gray, and so on. Okay, and then what you do get, you have to work out the details of the partial derivative matrix, but in fact, you do see that it's full rank, and therefore you get a lower bound of n to the d by 2, an exponential lower bound. Okay. So this is kind of nice, but it's actually even easier to see for a different polynomial. This polynomial. Okay, so this is called the product of inner products. Okay, for kind of obvious reasons. So imagine that you again have the same kind of setup. You have one red variable set and one gray variable set. Okay, and you pair them off, right? You have d by 2 of each of them, and you pair them off with each other, and you take the dot product between all pairs of them. Okay, and you take the product of all of these things, the product of inner products. Okay, so again, if you look at the partial derivative matrix of this, right, it's a product of a bunch of things on disjoint variable sets. So the partial derivative matrix is going to be a tensor product of these things. And we already saw some time ago that when you take a single inner product, a single dot product, its partial derivative matrix is just the identity matrix. So this thing is going to be a full rank matrix of size n. And so each of these things is going to have size rank exactly n. Since the ranks multiply, this thing is going to be rank n to the d by 2. This is again full rank. Okay. So this is again an example of a polynomial whose partial derivative matrix is as high, the rank of its partial derivative matrix is as high. Okay, so this is another example of polynomial that does not have any small. All right, so here are two polynomials, both of which for both of which we prove lower bounds using the partial derivative. The first of these polynomials is the polynomial we care about. The second of these polynomials is not something we care about, but it's notable because it's extremely simple, right? Because what is this, right? We always saw that this is a small expression, and we're just taking a small product of a bunch of small expressions. So this by itself is a small expression. Okay, so this polynomial, the one that we have at the bottom here, oopsie, sorry. So we showed lower bound for this one, but we also get the same lower bound for this polynomial, which by definition has a small expression, right? It's a product of things, and each of these things is a small sum of products. So it's what is called a pi sigma pi formula for this reason. It's product of sum of products, right? So this is a small expression, and this also has a very high rank partial derivative. We get the same lower bound. Okay. So this is on the one hand kind of comforting because it's a very simple polynomial, but on the other hand, it's also, I want to say, it's a little bit distressing. Okay, and the reason for this is that the notion of the rank of this partial derivative matrix, right, is supposed to capture the complexity of the polynomial. So the higher the rank is, we want the formula size to grow with it. But here's something that has a really small formula size, whose partial derivative matrix already has full rank, right? This sort of is a good thing for the technique because we're able to find these polynomials, but it's also bad because that means we cannot use this to prove formula low. Okay, because it doesn't really capture formula complexity in a nice way. All right. So Nisan, Wigderson already realized this. So how long do I go until the break?
Roughly 1 hour.
Roughly 1 hour. Okay, so I have 10 more minutes, and I can tell you a little bit about what Nisan and Wigderson did, and then we can take a break and come back and do the proofs. Okay. So Nisan and Wigderson, when they were coming up with this method, they already realized that this is a problem, right? So this example seems to be a reason where you can prove low bounds for sigma pi sigma formulas, which we already saw, but you cannot prove low bounds for, for example, things of this kind. Okay. So they said, okay, so let's introduce a new twist on this idea. And this new twist actually comes not from, it's not a completely new twist that they invented, but it comes from classical circuit complexity. It's a technique called the technique of random restrictions. Okay. So I just want to describe this technique to you. And to make things as simple as possible, I'm going to go to the first place where we don't know how to prove lower bounds like this and show how this technique is used. Okay. So now again, imagine that now we're going to deal with only the polynomial we're interested in. It's the iterated matrix multiplication polynomial. So we're multiplying d n by n matrices. And now imagine that we have a sum of terms. Okay. Now the terms are not products of linear polynomials like we had before, but they are products of quadratic polynomials. Okay. So I take these d variable sets that I have and I pair them off. Okay. And I want to stress here that it's important that in different terms in the sum could have different pairings. Okay, so in the first term, you could pair off x1 with x2. In the second term, you could pair off x1 with x3, etc., etc. So they're all different pairings. Okay, so I have a bunch of such terms, and each term is going to be a product of a bunch of quadratic polynomials corresponding to these pairings. Okay, so you can see that each of these sort of looks like this product of inner products polynomial. So potentially each of them could be full rank. Okay, so we have no way of controlling it. Okay, and so what Nisan and Wigderson asked themselves is, okay, how are we going to prove lower bounds in this situation? How do I lower bound the number of terms I have in this? Okay, and this already requires a new idea because you cannot simply use the partial derivative matrix because these matrices could be full rank in this situation. Okay, so how do you go about doing this? And this is this very clever idea of random restrictions. So the problem here is that all of these are quadratics, And it turns out that if you kind of squint and change things a little bit, you can make some of these quadratics linear polynomials, which you already know how to handle. Okay. So how did they do this? Well, what they said is the following. So imagine that you have these matrices here, right? D n by n matrices. So for each matrix, I'm going to do the following very simple substitution. With probability a half, I leave it as it is. And with probability a half, I replace this matrix by the identity matrix. Okay, so I just take these variables and then some of them are ones, some of them are zeros, and it just becomes the identity matrix, right? So what's the iterated matrix multiplication polynomial? So you're multiplying D n by n matrices together. And what's happening is that some of the matrices kind of become identity matrices, okay? And if you introduce an identity matrix in the between two matrices, then that just means that that matrix disappears, right? It just becomes a smaller product, right? So what you're doing is you're taking D matrices and roughly half of them chosen at random are going to become identity matrices. So what's going to happen is that this polynomial is just going to collapse to the same kind of polynomial, but on half the number of matrices, right? So you have D matrices. On average, you're going to converge to something like a product of D by 2 matrices, okay? And it's going to be a subset of these matrices. So maybe x1 goes away, and x2 stays, x3 stays, x4 goes away, etc., etc. You get a product on this smaller subset. Okay, so the polynomial that you care about sort of remains the same. It's the same kind of polynomial on a smaller number of matrices. Okay, so what happens to the stuff on the right? This is what is really interesting. So what happens in one of these terms here, right? So if I have a quadratic polynomial that's pairing up these two variable sets, there's a probability a half chance that one of these sets goes away and the other one stays, right? In which case, this quadratic sort of becomes like a linear polynomial, okay? And this is going to happen for roughly half the terms here because it happens probability half for each of them, okay? And so what you get is that these terms sort of simplify. They no longer have this structure here. They're not just a product of quadratics. They become a product of some quadratics and some linear polynomials, okay? And this, it turns out that you can use the partial derivative technique on this in order to again prove to. Okay, so we are now again in a situation where our previous techniques apply. So again, we do the same thing. We have a product of these matrices. So we kind of choose them to be red or gray judiciously so that the partial derivative matrix becomes full rank. So this side continues to be full rank. And on this side, what happens is that some of these terms are no longer quadratics, they become linear polynomials. And linear polynomials, we've already seen their partial derivative matrices have low rank. Yeah. So these terms typically end up having low rank. Okay, and that's sort of the story. Yeah. And so the left-hand side still has full rank. And what happens to the right-hand side is that you get a tensor product of these kinds of matrices. Some of them correspond to linear polynomials. And every time you have linear polynomials, instead of having rank n, the rank drops to 1. So you get a gain of n. Okay. So if you kind of work out the numbers, you expect about d by 4 and omega d of these to become linear polynomials. And so the rank that you expect is something like the full rank divided by n to the d by 4. So each of these linear polynomials causes a drop in rank, and then roughly d by 4 of them, that's a drop of n to d by 4. But this rank is a random variable, right? It depends on these random substitutions that we make. So there is some small chance, though an exponentially small chance, that all of these guys, each of the quadratics that collapse, maybe both of these get set to the identity matrix. In which case, instead of getting a linear polynomial, you just get a constant polynomial. Okay, so every time you have a pairing, either both of them go away or both of them stay. And when you do that, then the kind of term that you get is just a product of quadratics again, for which you cannot say anything. Okay, but this happens with exponentially small probability. And in that case, maybe you end up getting a full rank. Okay, so typically you want to get a polynomial which is far short of full rank, but with exponentially small probability, you get a full rank polynomial. Okay. And so now the expected rank on this side is much smaller than full, right? Whatever full is, it's some number. It's full divided by exponentially large numbers. So if you work out what comes as a result, the number of terms you need is something like 2 to the d. Okay, and you get a 2 to the d here instead of an n to the d because this is sort of the dominant term. Okay, does it make sense? So this technique of random restrictions is sort of to get the polynomial to a place where we can apply the partial derivative. Okay,
So,
and that's
so why probability 1/2? I mean, what happens if you change the probability from 1/2 to something else?
I mean, you could make the probability really, really small of survival, right?
Yeah.
So that would probably increase this thing a little bit, but then you would have to pay in the other term.
I guess you could balance it. So
No, yeah. So that's precisely the thing, right? Whenever you see a kind of when I look at this kind of analysis, it kind of gives me an itch in my back, right? Because I feel like I need to balance these two terms. And that's finally how we get the result to work. But it turns out that if you're only going to set matrices to identity matrices or leave them alone, then this is the best you can do. And intuitively, because there are only 2 to the d many distinct things you're doing, right? But because for every matrix, you can either leave it alone or set it to the identity matrix. So you have to introduce a third possibility. Yeah, and or many more possibilities. Unless you do that, you cannot breed this 2 to the d bound. So intuitively, you can never beat this bound using this technique. But you're sort of getting to the heart of what we want to kind of improve in this. Okay, but you're absolutely right. This balancing is bad. And what we do is actually balance out these 2 losses and get the right. Okay, all right, and that's it. So I've sort of come to the end of the first half of the thing. Yeah. So what did we do, right? So quick kind of summary of what we did. Our main aim was to prove lower bounds for these kinds of set multilinear formulas for this polynomial, the iterated matrix multiplication polynomial. And hopefully I motivated to you why proving low bounds for this polynomial is sort of important. Because proving the right low bounds here allows us to remove this condition of set multilinearity. Yeah, and if we could do that, that would be like, I think, the kind of an amazing result that we've tried to do for a long time, but we've not come close to yet. Yeah, and we saw 2 techniques that help us do stuff like this. Right? There's the partial derivative method that we use for proving sigma pi sigma low bounds, but it cannot be used to prove more general kinds of low bounds because of this example that we saw, the product of inner product example. And then we saw a way of getting around it, right, using these random restrictions. But now the dependence on n in some sense disappears, and you only get a dependence sort of independent. Okay, and this is sort of, it gave us still a 2 to the d lower bound. But if you work out the ramifications of this technique for more general kinds of formulas, you only end up getting a poly d lower bound. It's kind of a trivial lower bound. Okay, and this is sort of the result of Nisan and Wigderson that I told you about, which gives non-trivial lower bounds as long as you bound the nesting depth of these formulas. And so now the main innovation of our thing is to kind of modify this idea, like Rasmus said, to kind of balance out the 2 terms that we got in the random restriction analysis to get a super polynomial lower bounds for general formulas. Okay, and that's sort of the next half, which will be done on the board. So hopefully the board doesn't disappear and reappear. So we're in good shape, I think. Yeah. Yeah. Okay. Yes. Thank you very much.
Questions? Comments?
Yeah, very nice stuff. So, is there a break now?
Yeah, we're having, I mean, the first part will end as soon as we're done with the questions. And if we're done with the questions, then we have already ended. I don't know if we are.
So far, you didn't mention any specialty about the field.
It's a very good question, right? But then, what happens over finite fields?
Yes.
So, like everything that I'm going to say works over all fields. So, yeah, completely expressed on the side.
I never ever stayed the second half. I'm beat after
Okay.
1 hour. Just it's not because it wasn't interesting. Actually, it was very. I can't.
All right. Yeah.
So.
So, but what you're doing, like, are there any hope of, I mean, getting rid of this extra log?
Well, that's a great question. So I don't know what the limitations for technique are. So in some sense, we allow more general kinds of random restrictions to get the bounds that we get. And for the number of random restrictions we allow, it's still n to the log n is the best.
Okay.
But now there could be more things. And there are also other tricks that one can play here that I don't know how to use in our set. So there's things called shifted partial derivatives and other things. Maybe those come into the mix as well. So I don't know exactly. So, I mean, I don't see a straightforward way of doing it. So more ideas are required, but I don't see why not. So you will see the proofs are very, very simple. So I'm fairly hopeful that one can prove it. Good.
So let's thank. And let's take a break. Let's see.
Okay.
So we're back for the second half.
All right.
I need to switch off myself.
Okay. Still some sort of echo. Yeah.
So we're starting the second half, please.
Okay.
Srikanth.
All right. So I described already what we're going to do. Right, we're going to use the partial derivative method. We're going to use these random restrictions. But so far, I didn't really describe how to prove low bounds for general formulas. Right. So far, we are looking at like very simple kinds of formulas. We're looking at sigma pi sigma, and I think we went one step further. We went to sigma pi. And these are all sort of very restricted cases. And I didn't say at all how you get low bounds for general formulas that have no structure of this. So first, let me start off by saying that, because that's kind of a standard kind of lemma that's useful in a lot of these results. So the claim is as follows. So I would say that this claim is maybe in some sense implicit in some previous works, but I first saw it explicitly stated in this form in a survey by Spielka and Yabadayo. Right, and I think it makes life much easier, and it kind of abstracts out a part of the proof that otherwise would be annoying. So this one I think is really nice. So they said the following: let f be a formula of size s. Right? And when I say formula, it's always like set multilinear. So this claim is slightly more general there, right? And let's say it's computing our favorite polynomial, the iterated matrix product of n by n matrices. So that's fixed now. Okay. So it turns out that you can take this formula and you can write it as the sum of a small number of terms. Okay. And each term here is somewhat special in the following sense. It's the product of quite a few. In this case, quite a few is log n. Let me actually write it out. Let me write it as qi1, qi2, qi. It's the product of a lot of terms. Okay, so each individual term in the sum is sort of special in the sense that can be written as a product of log n set multilinear polynomials in disjoint sets of matrices. Okay, so for instance, this might depend on the first and the third, and then this one would depend on the second and the fifth and the 10th, etc. But of course, overall, the log n set sets and they cover all the matrices together. Okay, so the matrices is sort of partitioned into log n parts, and each of these polynomials depends on one of these parts. Okay, and that's each term. And in different terms, you can have different partitions of the matrices into log n parts. And then you have a product of polynomial in each of the parts.
Are you saying anything about the size of this guy now,
right,
or no? It's,
yes,
that could be.
So you have a size S formula here. Thanks a lot for bringing that up. And that's exactly the number of terms.
Yeah, but the overall circuit that you have here.
So there, I'm not saying anything. So
yeah,
these polynomials, it turns out that if you stare at the proof, you get that these polynomials themselves have formulas of size S.
okay,
But it's not something that I'm going to use at all from now on.
okay.
So the size of the formula only comes up in the number of terms in the sum, as far as I'm concerned. And from now on, for me, these polynomials are arbitrary.
So again, so we're starting with there is a set multilinear formula of size S,
right,
and then just partition it into these S sums.
Yeah.
And we're gonna get something like what? Something like S cube all in all, or
so there is no
but
S,
like highly structured, because you said
right,
the QIs.
They do have formulas of size S, you're right. So if you write it out, these individually would give
S squared log n.
Yeah, S squared log n or something like that. But we're not going to use that at all.
Yeah.
But you're right. These individually have formulas of size S. So
but like with a slight further blow up, you get something super structured.
Get something
That's
very
how to think
structured.
about it.
Right, very structured. Right. Okay. So this is, and what we're going to show is that any decomposition of the iterated matrix product polynomial of this form must require that S is very big. Okay, we're not really going to care about the kinds of polynomials you have here. I'm going to say that S is very big.
And again, the partition, do you have like the QIs can depend on?
So each QI depends on its own. Each QI1 depends on some subset of the matrices.
Yeah.
QI2 depends on a disjoint subset. QI3 depends on a disjoint subset, etc., etc.
And you don't care about the sizes of these?
I don't care about the size of these. I could say something if I wanted to, but I don't. I just care that these are all non-empty, right? I don't have like a bunch of constant polynomials. Each of them actually depends on something.
Okay, that's important.
That's important. Right? So there's a non-empty subset inside each of these QIJs, but that's about it. Yeah. Yes.
What happens if you remove this multilinear restriction in the beginning of F?
Right.
still get a similar result, but with less restriction. on
Right.
the
So
law.
then these individual polynomials are not going to be set multilinear. They will be something else. There will be arbitrary. There will be polynomials which are non-set multilinear.
And you don't have the partition of the.
You don't have the partition of the variables.
Okay. Almost
Right.
everything.
Yeah, yeah. So it's going to be important that we have all that. Okay. That makes sense.
So the claim is saying that if you have such a formula, it has a chip.
Yeah. So if you have a formula, you can write the polynomial computed by the formula as a sum that looks like. So you'll have to rewrite the formula a little bit. You have to play around with the formula, but you can turn it into one that looks like this. And from now on, we are going to only worry about this decomposition. And we're going to look at the number of terms. Yeah. Okay. Good. And so now we're going to stare at this, and now we're going to use the partial derivative method and random restrictions to bound the rank of this guy. Right. And now just to kind of quickly get it, right? So this now starts to look a lot like the things we saw already, right? It's a sum of product of things. And so we can kind of use the same machinery to analyze. So if I look at one of these guys, right? So it's partial derivative matrix, let's call that maybe MI. What's that going to look like? So it's going to be the tensor product of these individual partial derivative matrices, right? Going to be the tensor product of these things. And so what we're going to do is we're going to stare at this. We have no idea what these polynomials are. And so it's going to be hopeless for us to analyze the individual partial derivative matrices and say that they're low rank or high rank in any reasonable way, because these are polynomials adversarially chosen as far as we're concerned. Yeah. So from now on, the only thing we're going to care about when it comes to analyzing a term like this is the shapes of these partial derivatives. Right. So we're going to look at each of these matrices. So maybe Qi1 depends on x1, x3. Right. So we're going to take some of these variables and make them row variable sets. Some of them are going to be column variable sets. So maybe x1 ends up as a row variable set. So then the shape of this matrix is going to have x1 many rows and x3 many columns. It's going to look like that. Right. And maybe Qi2 depends on x2, x5, x8. Right. Which means that the second partial derivative matrix is going to look like, I don't know, let's say x2 and x5 are row variable sets, and x8 is a column variable set. Right, so each of them is going to look like that. And now we want to say that there is a kind of a way of choosing these row variable, column variable set partitions to make all of these MIs low rank. So the whole thing adds up to low rank. Okay. And the important thing is we don't understand which polynomial has x1 and x3 with it, right? And different terms in one, x1 may be paired up with x3, in another, x1 may be paired up with x2, etc. We have no control over this, right? That's all decided adversarially as far as we're saying. Going to say no matter how it's decided, we're still going to be able to prove lower bound after some random restrictions. Okay. So now, in order to prove this lower bound, we will look at random restrictions. But in the Nisan-Wigderson case, we had only two things we were doing. We were leaving this matrix alone, or we were setting it to the identity matrix. That is all we were doing in Nisan-Wigderson. But now we're going to do something else. So this is NW. But now what we're going to do is we are actually going to project this set of variables into a completely different set of variables yi. Okay, so xi is going to turn into yi. I'll tell you how a little bit later. That's towards the end of the talk. But as far as we are concerned, for now, what we're going to do is we're going to choose the sizes of these yi. Right? Because that's what's going to determine the shapes of these partial derivative matrices. Right? So now all of these become just y variables. Okay, so I turn my polynomials into set-multilinear polynomials in other sets of variables. Okay, so y1 to yn are going to be disjoint sets of variables again, so new, completely fresh variables. And now the size of yi is not going to be the same for every I. It's going to be some chosen parameter alpha. Okay. And you should think of alpha I as some, so this is some number between 1 and n, or maybe 0 and n, right? And eventually we choose it to be a power of 2. Yeah, we choose the set to be a power of 2, but for now just think of alpha I, this exponent, as being something between 0 and 1. That's all that matters. Some exponent between 0 and 1. And these alpha i's are what are going to determine our random restrictions. Okay, so our random restrictions are going to be determined by the sizes of these sets. Okay. And
Think of them as smaller sets.
they are smaller than n, right? Because we start with matrices of size n by n. So we're going to project to sets of size smaller than n, but there could be much smaller or much bigger. So there's going to be all sorts of imbalances. So you think of Nisan, Wigderson as choosing only two possible values of alpha I. Either alpha I is 0, in which case we get to the identity matrix, or alpha I is 1, in which case we get to the whole thing. But now we are allowing ourselves the freedom of alpha I going between 0 and 1. And it's this additional freedom that will allow us to prove stronger.
But in order for this to make here, you're using set multilinearity, because otherwise I could, like, if I start getting collisions inside my variable sets, then
Right.
multilinearity would go out of the window, but set multilinearity stays. Is this right?
Oh, right. Oh, I see what you mean. Yes, that's right. If it was just multilinear, that's right. That would go out the window. If you did, you're right. So I use set multilinearity all over the place, even in just kind of doing this decomposition, right? To understand the sizes of these partial derivative matrices, I'm using set multilinearity.
Okay.
So it's kind of hidden all sorts of parts of the problem.
Okay.
Right? But you're right. What you're saying is also a problem. You would get collisions for, yeah, you would have to be careful if you're doing multilinear. Okay, so this is the additional freedom, right? Over and above Nisan, these set sizes are going to be here. Okay, and so now I can kind of tell you what these, how this restriction is chosen. It's pretty simple. It's kind of so how do I choose this restriction? So I want to see if this is visible. Oh, yeah, okay, it does seem to be visible. All right, good. So choosing the restrictions. And so this restriction, as I said, you want to choose the sizes of these yi's, right? But I also want to choose whether these yi's go to the row side or the column side. Okay, and it's actually going to be kind of from a technical point of view, it's going to be really nice to think of these alpha i's not as distributed between 0 and 1, but as distributed between -1 and 1. Okay, and the alpha i's being negative sort of means that we are putting it on the column side. The alpha i's being positive sort of means that we're putting it on the row side. And the absolute value of the alpha i's, that's what's going to kind of tell us that what the size of the variable is. All right. So now I'll tell you how to choose the restriction in a moment. But once you've chosen these numbers, right? So if you look at the overall polynomial, right? So all the variable sets together. So what's the dimension of those things? So how many rows do we have? We have all the alpha i's that are positive kind of correspond to a number, to rows, right? And the rows sort of multiply out. So what we're going to get is n to the I positive alpha I. So I take all the positive alpha I, I sum them together, and I raise that with the base to an exponent with base n, and that gives me the number of rows. And the number of columns is going to be the same kind of thing, I negative, and I have minus alpha. Right, that's the number of columns. And finally, I want my hard polynomial, the iterated matrix multiplication polynomial, right? I want it to be full rank. So finally, I want this matrix to be a square matrix. Okay. So however I choose these alpha i's, I want the positive guys and the negative guys to cancel each other out. Okay. So the sum of all the alpha i's needs to be 0. Okay. So I'm going to choose my alpha i's in a certain way. They're going to be positive or negative. They're going to be bounded. And the sum is always going to be 0. Okay. That's kind of how I'm going to choose it. In fact, I'm going to choose it to have an even stronger property. So let me describe how to choose it. So imagine that I choose these alpha i's, right? So let me track what happens. So I'm going to choose the alpha i's one after another. I'm going to choose alpha 1, I'm going to choose alpha 2, I'm going to choose alpha 3, etc. Let me keep track of the sum of these numbers as I choose them. Okay. So I start from 0, because before I've chosen anything, and I want to end at 0, because I want the sum of all of them to be 0. And what we will ensure is that at each point of time, the sum sort of doesn't become too positive or too negative. So the sum stays between 1 and -1. Okay. So we choose alpha 1, maybe we go up here. Choose alpha 2, maybe we go down there. We choose alpha 3, maybe we go down there, but that's maybe too negative. Then we choose alpha 4, we go up here, etc. Okay. So the graph of these alpha i's is going to be, the sum of these alpha i's is going to go up and down. But at all points of time, it's going to stay between -1 and 1. So you're never going to become too positive or too negative. And then at the end, I'm just going to, the last guy, I'm just going to choose to be whatever is required to make the whole sum 0. Okay, so that's how we choose it. And now, contingent upon doing this, any reasonable way of doing things will work. So here is the one way. So for I equals 1 to n, right? Here's how I choose the alpha I. So look at the current sum. So let's say the current sum S is the sum of all the alphas I've chosen so far, all the alphas I've chosen so far, right? If the current sum is negative, then choose the last alpha I to be positive, right? And positive, it can only be between 0 and 1, so choose it to be positive. Okay, and how do I choose it? Just choose it to be a random number. Okay, strictly speaking, we need n to the alpha I to be a power of 2. But let's not worry about that. It doesn't make much difference to calculations. I just think of it as a random number between 0 and 1. If S is positive, then choose alpha I to be a random negative between -1 and 0. Okay, and that's it. So that's the restriction. So the restriction is that, so currently I'm just telling you how to choose the sizes of these sets and whether they're row sets or column sets, and this is how I do. Yeah. Does it make sense, the definition? Yeah. I also have to say that the last guy, alpha n, is going to be just it's going to be whatever it needs to be, so that the entire sum is equal to. So that's just for the last guy. Yeah, so this is for I equals 1 to maybe n minus 1. Yeah. Okay.
You said that any way in which this graph stays in relation to this probably works.
Right. So you will see what we use about it. We use very less about this method of choosing the random restriction, but we need, it can't be like a fixed. So of course I could also choose this graph, these alphas just to be fixed numbers, right?
Yeah.
So that won't work. You need some amount of randomness, and you need these alphas to not put too much mass inside a very small interval.
Okay.
So, you could choose any other way of choosing alphas that has this feature. But you will see, we use very less about it.
Okay.
But we need something. So they can't be fixed. So in Nisan and Wigderson's thing, alpha I could only be 0, 1, or -1. So that's too discrete for us because that puts too much probability mass at single points. So it needs to be somewhat like a continuous distribution in some sense. More continuous. That's all we use. Okay, any way of doing that in a reasonable works. All right. Okay, so that's our choice of restriction. And that's it. So now that this is in place, we can actually just analyze the ranks of these matrices. Okay. So I have to show you two things. I have to show that this right-hand side collapses to something that's not full rank, becomes low rank. And I also have to tell you how the left hand, the hard polynomial that we have, it remains full rank. Okay. And that's actually going to involve us not just saying what the sizes of these variable sets are, but how to substitute these xi's by the variables in the yi's for it all makes sense. So I'll do that last. I'll first do this thing where I just analyze the right-hand side. This just requires the sizes of the variables. Okay. So let's take one of these terms, right? It doesn't tell you much of which one we take. We want to say that each of them has low rank. So let's take maybe one of them. So let's say Q is Q1 times Q2 times Q log n. And maybe Q depends on a subset of the matrices, maybe S1 is a subset of n, S2 is a subset of n, S log n is a subset of n. These are disjoint subsets whose union is all the matrices that we care about. Right. And so let's look at the rank of the matrix corresponding to Q. I'm just going to call it rank of Q. Right. And we know already that the rank is the product of the ranks. Okay. And I want to say that this quantity is much smaller than full rank. Okay. And so let's compare it to full rank by just dividing by the full rank. Okay. So what is full rank here? It's a square matrix. So the full rank means either the number of rows or number of columns. Okay. So here I'm going to make a small stupid technical trick, but it makes life much simpler when I do this. So instead of writing either the number of rows or number of columns here, let me write the square root of the number of rows and the number of columns. Okay. It's not doing anything. They're both the same. So it's just the number of rows and number of columns. Yeah. What's the advantage? Well, the advantage is that this is sort of multiplicative, right? Because when you have a tensor product, the number of rows is the product of the number of rows. Number of columns is the product of the number of columns. So I can write this as the number of rows in this matrix, in this partial derivative matrix, times the number of columns in this partial. so let me just rewrite this. So it's a big product. I going from 1 to log n. Okay. All right. So now you'll see why imbalance helps. Okay. Imbalance helps because we're kind of comparing the rank to this quantity here. Yeah, this quantity is sort of like, so it's like a measure of area, right? The number of rows and the number of columns is a measure of area. So if you have like a long skinny matrix, right, then its rank is going to be at most the number of columns, which is much smaller than the area. Similarly, if you have a very short fat matrix, rank is going to be much smaller than the area. So when the rank can be equal to the area is when you have a kind of square matrix. So if you have imbalance, you're going to fall short. Okay. So let's just say that. So look at the rank. So the rank is, by definition, it's the minimum, it's at most the minimum of the number of rows and the number of columns. Right? And at the bottom, we have the product of both the rows and number of columns. So I can think of that as the product of the minimum and the maximum. Right? So I have just the minimum here, and I have the square, the geometric mean of the minimum and the maximum of the bottom. Right? So what is this? Say the square root of the minimum and the minimum here. So I can kind of do a little bit of algebraic manipulation, and this is just the square root of the minimum by the maximum. Okay. So kind of an imbalanced matrix where the minimum is much smaller than the maximum creates a big problem. Right? Okay.
Sorry,
Yeah.
jumping a little bit ahead backward. So far, it didn't tell us what is the size that each QI in the size of matrices, the number of matrices that each QI depends on. You
Yeah.
don't want them to be any of them to be too large.
No, I don't care. All I need is that all of the sets are non-empty. Every QI depends on at least one matrix. So I don't really care. So it could be that one of the QIs depends on like n minus log n matrices, and all the others depend on one each.
So you only need that none of them is empty.
Empty. That's it. That's all the people need.
Otherwise, for example, just one QI is F, then we're done.
That's right. We need each of them to depend on at least.
So this is what you.
That's right. That's all they're going to use. Okay. And we'll see how now. Okay. So let's look at this thing, right? So this is the minimum and the maximum. And I can write that in terms of these alpha I parameters that we chose, right? So imagine that you take one of these terms, right? And let's say the minimum is the row side, minimum is the column side, right? The column side, and the maximum is the row side, right? So then this quantity is going to be, so the minimum is going to be n to the, I sum all the negative guys, right? That's the minimum. And the maximum is going to be right? So it should be the negative, but just in the, so let me, okay, I'm reusing I here. Let me use a J up here. So J in negative for J, J in positive alpha J. But I only want the negative and positive that come from the ith term. Right? The negative part of SI and the positive part of SI. So these are the two things that show up. And so, and of course I have a square root over the whole thing. So this you can rewrite as just 1 over n to the, so let's write it this alpha J, right? Because I'm just summing all the positive guys, and if I bring this down here, I'm just summing all the guys, right? I'm just bringing this negative exponent down here, so now I'm just summing all the guys. So I'm summing all the guys in SI, and I'm dividing by 2, right? And these are random numbers between -1 and 1, right? So I'm summing a bunch of random numbers between -1 and 1. So in general, I expect this to be not very close to 0. I expect it to be bounded away, maybe like -half, maybe like or +half or whatever. So as long as it's bounded away by 0, this quantity is reasonably big, right? And you get essentially a 1 by n to the something. And if we got that 1 by n to the something in each of these log n terms, then we'll get 1 by n to the something log n times, and that's 1 by n to the log n. And that would be the kind of bound we want. Like that's the hope, that's the dream, right? We're not quite able to get that, but we'll be able to use this to get a super polynomial. Okay, so in general, what you can show is that the ith term here, the corresponding loss in comparison to full rank, right, is this quantity. It's the sum of the numbers inside Si, right? So for instance, in this graph here, if Si contained maybe the second guy and the fourth guy, then I would take these two numbers and I would sum them together, and that's the sum that shows up inside this absolute value, right? And as long as that sum is not too close to 0, we are good. Okay, and that's the quantity we're trying. So that's it. So let's look at this number, right? So now it's a product of all these guys, right? And let's look at the expected rank.
So far, the +1 -1 0 would work fine.
So far, yeah, everything. So here, this would work for any choice of the alphas.
As long as they're
between so far we haven't even used that.
Yeah.
Right? We've not used anything. So the alpha is being bounded between -1 and 1 is going to be useful when we try to argue about the iterated matrix multiplication polynomial. So we've not used that at all. But now here what we are saying is, so and as you said, yeah, you could choose the alphas to be -1, 0, or 1, and everything would work out. But now when we look at the expectation, that's where we're going to use our choice of random restrictions. Okay, so we're looking at the expected value. So again, this is expectation rank 1 by whatever full rank is, right? We wrote down a technical term for it, doesn't really matter. This thing. It's the square root of the number of rows times the number of columns, which is full rank. Right? This is the expected product of all these things. Right? It's at most the expected product of these quantities up here. Right? And let's look at it, right? Let's say that at least half of these quantities, so there's one for every SI. Let's say at least half of these quantities is at least epsilon. Right? Let's say at least half of these numbers are at least epsilon. Right? In that case, this quantity, each of these quantities would contribute a 1/n to the epsilon by 2. Right? I'm told you what epsilon is. We'll figure that out in a bit. But if at least half of them were epsilon, so each of them would contribute, each of the ones that are at least epsilon would contribute 1/n to epsilon by 2. And since half of them are epsilon, they're at least log n by 2. Right? So this is kind of the good case for us. We expect that not too many of these quantities are going to be small. So if at least half of them are at least epsilon in absolute value, then the bound we get is 1/n to epsilon log. Okay, so this is the good case, right? But this is a kind of a completely random restriction. So anything can happen, right? It could just happen that all of these quantities end up being 0, right? And in that case, the rank would be full as far as we are concerned. We have no control over this expression after that. So there's some probability with which things go completely south, in which case we just say the rank is as big as it can be. So full rank. Okay. But this happens only with a small probability. Yeah. So what's the bad event here? The bad event is the probability that at least half the SIs have bias. Bias is this quantity here, have bias at most epsilon. Yeah. So half the SIs, so each SI takes a subset of these terms. So at least half of them somehow magically happens that these random numbers almost completely cancel out. You get essentially 0. Okay, or at most epsilon. Okay. And let's look at the probability of that, right? So this is where this random restriction procedure comes in. So how did we choose the random restrictions, right? We chose these alphas 1 by 1, right? Let's look at, for instance, S1, right? It's got a bunch of terms. If I look at the terms in S1, I have S1 contains maybe, let's say, the second number and the fourth number. Let's condition on what the second number is. Yeah. Conditioning on what the second number is, and let's also condition on the third number, for instance. Now, the fourth number is either going to be randomly distributed between 0 and 1, or randomly distributed between -1 and 0. So what's the chance that the bias lies inside this very small interval of length like epsilon? Right? So since the number is uniformly distributed between an interval of length 1, the probability that it lands in an interval of length epsilon is at most epsilon. Right? So for this thing to happen for any given set, the probability of it happening is at most epsilon. Right? And now if you look at all these sets together, you can kind of just condition on them one after another. Look at the last element of S1, the probability that that's bad is at most epsilon. But now condition all the way until the last element of S2, the probability that something happens there is at most epsilon. So for each set, the probability that something bad happens to that set is at most epsilon. The kind of independent events, because you can condition on all the alphas before the last element of that set and kind of multiply another epsilon. So this quantity is at most essentially epsilon to the number of bad events that happen. That's like log n by 2. Yeah. So for each sort of collection of the SI, the probability that something bad happens, for each SI, the probability that something bad happens is epsilon. And things are kind of independent because you can condition on all the elements until the last element of that SI, and then you still get a probability of epsilon. So you can, by this conditioning argument, you can get like epsilon to a number of bad events, that's log n by 2. Okay. So that's it. So that's the whole bound. So there is something, is either something good happens, in which case the rank is small, or something bad happens. That something bad happens with very small probability, right? And now these two events are kind of trading off against each other, right? If epsilon is big, then this quantity is always small. Okay, that's good for us. But this quantity might be too big. So if epsilon is like half, for instance, then this quantity is 1 by n to the log n. That's great. But this is like 1 by polynomial. It's not so good. Because this is like this only gives you like a polynomial lower. So what you want to do is you want to choose epsilon to kind of balance these two terms out. And if you choose epsilon to be the right thing, then you get, so I guess epsilon something like log n by log n will do. This implies that you get something like 1 by n to the log. Okay, so you kind of, there are two terms here. If you balance them out, then you get the right bound, the bound directly, which is 1 by n to the log. Yes.
No, I'm a little confused.
Yes.
If each, for example, only except the last one, all of the QI in your product depend only on one matrix.
Yeah.
And how does the dimension decrease counting goes?
So let's say every QI, let's say all the QIs except for one, then that case is actually very simple. Let's say the first QI depends on almost all the matrices, and all the others depend on one each.
Yeah.
Right? So in that case, what is this quantity, right? So in that case, the quantity, yeah.
I don't see, well, for example, Q1 depends on X1 and X1 is put into, let's say 1 is put into the row variables.
Right.
It seems like you're claiming that the rank is now 0.
Q1 depends on X1, and sorry, can you repeat your question?
The question is, suppose Q1 depends on X subscript 1.
Just that, nothing else.
Nothing else.
Okay.
And then after a random restriction, you're counting its dimension contribution to the product.
Right.
And you say, I mean, previously it is, or if I understand correctly, it's okay. How does the rank contribution change
right
before and after a restriction to Q1?
Right. So if you look at Q1, right, the rank of, so if Q1 contains just one variable set, then it's either the partial derivative matrix, either a row vector or a column vector, right? So then the rank is just 1, right?
And the decrease of.
So the decrease would be 1. So you would get 1 divided by, let's say it contains, there's just one column. So then it would be 1 over square root the number of rows.
You're over square root of 0.
No, number of columns is 1, right? Because you still have a single column, right? So if you have a partial derivative, if you have a matrix Q that just depends on X1, right? So it's partial derivative matrix. So let's say this is a row variable set. Its partial derivative matrix is going to have as rows labeled by all the variables of X1. Yeah. And the columns are labeled by monomials in the column variable sets. Okay. In this case, there are no column variable sets. So the only monomial in the column variable sets is the empty monomial.
That's a 1.
That's a 1, right? So that's just 1. Right. So in this case, you don't get like a, yeah. So you get some non-trivial matrix. So in this case, number of columns is 1, and the number of rows is whatever it is, the size of the set. Right. So in this case, it would be just n to the alpha 1. And now we are asking what's the probability that alpha 1 is less than epsilon? Yeah, which is at most epsilon.
So what is the rank of QI? Q1 is 1,
Yes,
and you are letting 1 over 1.
1 over this product, right? So we are comparing what is full rank for us. Full rank is like the geometric mean of the number of rows and the number of columns. Right? So in this case, as you said, you have only 1 column, but you have lots of rows. So when you divide by the geometric mean, you're dividing by a big number.
Rows I and
Yeah, so this is the number of rows in the partial derivative matrix corresponding to Qi. Right? So in this case, you'll be dividing by the square root of this times this.
there's another large number.
That's a rather large set. Right? Yeah, so the definition of full rank kind of changes when you look at these terms individually. Of course, for the whole thing, it's just the number of rows or the number of columns. But when you multiply out, this thing is actually like the square root of the 2 quantities. So for a matrix which is very tall or very fat, it is much larger than the maximum possible rank. Yeah, and that's sort of our game, because we have no idea how to bound the rank of the matrix in any non-trivial way. We can only use the shape. And in this situation, this is how we use the shape to get to say low rank.
And you're assuming that there are lots of rows in Q1.
I'm assuming that, yeah, so there's a bad event that Q1 has very few rows.
That's like 1.
Yeah, let's say just 1 row, but that happens only with probability like 1 by n. Okay, that means that alpha 1 has to be a very small number.
The thing is, originally you don't have control of how many monomials are there in your Q1, right?
That's right, but I still know the sizes of the sets, right? This is all I'm playing around. So if Q1 depends on x1, what's the probability that there are hardly any variables in x1 remaining?
Q1 could depend only on one monomial. Yeah.
That's true, but right, right. So absolutely. So when I say Q1, I'm saying that Q1 is a polynomial in the whole variable set x1. Now Q1 could choose to depend on only a small number of variables inside that. Then a large portion of the partial derivative matrix would just be 0. But still, you would have to write down the whole partial derivative matrix. So the matrix is still defined by the sizes of the variable sets that Q1 is defined on. If it focuses on only a small subset of those variables, then that's Q1's loss. And it's going to lose out when we measure the rank. Yeah. So when we look at the rank of the partial derivative matrix, we don't say, oh, how many variables do you individually depend on? We just say, okay, these are the variable sets that you're supposed to depend on.
So you're counting the
Yeah.
supports.
Yes.
Not about Q1.
Yeah, not about Q1 in particular. That's true. So in any such term, x1 is the responsibility of one of these things. And wherever, whichever one sort of takes the responsibility for x1, all of x1 appears in that partial derivative. Okay, thanks. So I guess, are we doing that time? Or we have, what do we have, 9 minutes remaining?
Yeah, I mean,
Yeah.
it's not like, it's up to you on 5, 15, 20, probably not more than 20 minutes.
No, I will try to do it in less than 9 minutes. Okay. So the last part is that we need to say that the iterated matrix multiplication polynomial does not drop. It still remains good. Okay, that's the last bit. Okay. And this part is just, I don't know what you want to call it, theory of computation, automata theory, or whatever. That's all this is. So from now on, there won't be any computations. Hopefully, I'll just get the. I will let pictures stay 1,000 words. Let's see if I can manage to do that. Okay. Okay, that's it. All right. So let's look at this polynomial that we care about, the iterated matrix multiplication. Okay. So again, you have a bunch of matrices, x1, xn. We multiply them together. Okay. Each of these is an n by n matrix, and we look at the top left term. Let's say the 1, 1th entry of the product. Okay. So what does this polynomial look like? So far we never had the reason to write it down explicitly, but now we have some reason to write it down. Okay. So it looks like this. So if you expand it out and write it out as a sum of monomials, Well, you're looking at the 1th term. So in the first matrix, you want to take some entry from the first row, right? And depending on which entry you take from the first row, you want to take that row in the second matrix and then take some entry from that row. And then you want to take that one from the third matrix, etc., until you go to the nth one. And now you want to take the first column because you want to output the 1, 1. It's a sum of all. Okay, so this polynomial is the sum of all monomials that look like this. So the column of the first variable, the column of the variable from the first matrix matches the row of the variables in the second matrix. Yeah. So an interesting thing about the set of monomials that appear in this is that if you look at just the monomials that appear in this, right, they have this nice property that they can sort of be checked by a finite automaton or a streaming algorithm, depending on how you want to talk about it. So if you imagine that a finite automaton is given some monomial like this, right? It's given some monomial, one variable, the first variable from the first matrix, the first variable, some variables from the second matrix, etc., etc. If this automaton is tasked with checking if this monomial appears in this expansion or not, there's a very simple automaton that does this. Because what does it need to do, right? It looks at the first variable set, and then it remembers this I1. Then when it gets a second variable, it matches up. It sees that the first index here matches up with this I1. And if it doesn't match up, it rejects. If it matches up, then it stores this I2, then matches up this with the third variable, etc. Okay, so I can draw this automaton like this. So I have a start state. And depending on what the first variable is, I have x1. Right? Depending on what the first variable is, I go to different states. Maybe 1, 2, blah, 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 n. Okay. And now, so coming here means I saw x1, 1, 1. So I saw the 1, 1 entry. And now I get the second variable. And what I want to do is I want to match up the second variable with the row index of the second variable with what I've seen here already. Right? So if I'm in the I1th row here, for instance, then I only look at variables which have I1 as the row index. And assuming that I1 matches up with this guy, I go to the I2th state here. Right? So I have this kind of finite automaton, which has this kind of property. So I know some of you are doing this course on algebraic complexity theory, so you may have seen this thing called an algebraic branching program. So this is what an algebraic branching program is. It's just like an automaton that sort of looks at the monomial and sees whether it sort of comes from the polynomial you're interested in. Okay, you're also allowed to do some other stuff in an algebraic branching program, but here we just have this automaton. Okay, and this is sort of a very nice automaton here because all the edges here have distinct variables on them. Right, so if you have going from 2 to 1 here, you have x2 to 1, etc. So the edges are all distinct. Okay. So what we are going to do in order to kind of get hardness for iterated matrix multiplication is that when we choose these new variable sets, y1 through yn, we're going to define a new polynomial on these variable sets, y1 through yn. And that's also going to have a small automaton. Okay, so maybe it has an automaton that looks like this. Okay, so you have some variables among the sets y1 here, and some variable sets among the sets y2 here. Okay, we're going to define this polynomial, right, which is going to be full rank, and it's going to be defined on y1 to yn. Okay, and now to get hardness for this guy, what we're going to see is that this automaton, of course, can be obtained from this automaton by just setting variables to 0. Right, because so for instance, if I have an automaton like this, I can just kind of excise this entire part by just setting all these variables to 0, and I can kind of get this automaton sitting inside that. Okay, so as long as I can embed this automaton inside this one, then I can sort of also find the same polynomial inside this by setting some variables. Right? So all I need is that this automaton has at most 2 states at every layer, or whatever, at most n states at every layer, so I can sort of embed this in there. Okay, because any automaton with at most n states in every layer can sort of be embedded in here. You set some other variables to 0, you identify some variables and it goes. Okay, so I'll define now a hard polynomial in these variables. Okay, it just have the property that it's kind of checkable by this algebraic branching program. And once you have this, you can kind of project down it. Okay, so that's it. So let's go ahead and do that. So how are we going to choose this polynomial? So we have some row variable sets and some column variables, right? So maybe let's say, so in the picture that I've drawn here, the first entry is positive. So the first one is a row variable set. So let's write it down. You have row variable sets and column variable sets. So you have the first one, which is maybe y1, the row variable set. Okay, and I've drawn a box here, which sort of indicates the size of y1. Okay, so I'll assume that the size of y1 is n to the alpha I. Yeah, which is like a power of 2, which is like 2 to the alpha I log. So this is the size of the y1. Then the column variable set maybe is y2, and then I have another column variable set, maybe y3, and then I have a row variable set, which is y4, or something like this. Okay, so now let me define my polynomial. So in order to define the polynomial, I'm going to say what are the variables inside these sets. I'm going to assume, since these are all powers of 2, I'm going to assume that the variable sets, they're just kind of labeled by binary strings. Okay, so every variable sort of its name is a binary string. Okay, and I'll just use, because there are lots of numbers floating about, instead of zeros and ones, we use A's and B's. So I might have a row variable A, B, A, A. Okay, this is a variable. Okay, and then I might have another variable in this variable set, A, B, B, and so on. Okay, so what that means is that every row monomial, yeah, monomial is a choice of a variable set, a variable from each of these row variable sets. Every row monomial is just a string, a binary string. Right? It's just a binary string. So I have here A, B, A, B, B, and so on. These are some binary string. So in my partial derivative matrix, the rows are all labeled by binary strings in A's and B's. The columns are also labeled by binary strings in A's and B's. Okay, and I want to set it up so that this matrix is full rank. Right. So what's the simplest way of doing that? Let me just make it the identity matrix. Right. So I just wanted to ensure that the only monomials in my polynomial are those for which the row monomial exactly matches up with the column monomial. Okay. And this can be easily checked by an automaton. Okay. Because what are you going to do, right? You're going to look at the row variable set. You're going to kind of say, okay, I got this string as my row variable. And then when I get a column variable set, I'm going to match off the row variable set with the column variable part. I might have some leftover part. I remember that. I get another column variable set, I match off with that. Then maybe I have some leftover, I match with the next row variable set, etc. Yeah. You just need to convince yourself that you don't need too much memory in order to do this finite automaton construction. And that's exactly this condition of being bounded between -1 and 1. Okay, this condition of being bounded between -1 and 1 ensures that at any point of time, there are not too many more row monomials than column monomials. Yeah. So at all points of time, you're going to have only a slightly more row monomials than column monomials. And this is going to ensure that the amount of memory, the amount of stuff you need to remember about the row variables to match with the column variables, or about the column variables to match with the row variables, that amount of memory is always going to be bounded by log n bits of memory. Okay, and that's sort of what this sum being bounded between -1 and 1 entails. And that means that at any point of time, the number of states in your automaton is at most going to be n. You're never going to need more than n states. And if you're never going to need more than n states, you have this automaton with at most n states at every level. You can embed it here, and you've reduced kind of this problem to iterated matrix product. And since you've embedded it in this, that means you can kind of do substitutions to this polynomial to make it full rank. Yeah. And those are the substitutions that we finally need to do here in order to make the entire random restriction go through. Okay. So in the Nisan Wigderson case, there are only one kind of substitution. You either leave things alone or you substitute by the identity matrix. But here we have a more involved kind of substitution. The kind of substitution that's required to embed this automaton inside this, or this algebraic branching program inside this. And once we make the substitution, we get a full rank polynomial. This matrix is full rank. This one is small, it's not full rank. So that's the, okay. But yeah, been a long 2 hours. Stop here. Yeah, thanks.
Maybe one last question or remark is that still, it seems a little bit, it seems interesting to me that one point of the lemma is that you shouldn't decrease log n. The fact that you have log n many products really helps you. If you have two products, you die.
You die, exactly. But because being a product of log n things is more special than being a product of two things, right?
Actually, if it is two, then you could write a product of two.
That's right, absolutely.
You use your recursive.
Exactly. That's right. That's
In the
exactly
log n, you need into the log n, something like
That's
that.
right. That's exactly right. That's why we believe that into log n is kind of tight. That's another reason. We believe that even with this decomposition, you should be able to prove an into the log n lower bound. We don't know how to do that.
And you think the problem is this analysis or you need some other?
Yeah, so the kind of random restriction we have, we still are only allowing, so as I said, right, the only powers of 2. So they're only like log n possible sizes of these yi's, and that's sort of a bottleneck. So for these restrictions, we know that we have the right over into log n. So somehow maybe you could allow more yi's, I mean more sizes, intermediate sizes. And the hard part seems to be that it's not clear how you would argue that things are low rank in some sense. I mean, so yeah, there's not sort of enough space in between. We don't know how to take advantage of the fact that the size is not a power of 2 but some intermediate number. We don't know how to. Yeah, we don't know how to analyze things and show that they're low rank. Just using these dimensions, it's not clear that we do that. Yeah, there seems to be something like it.
Okay.
Yeah.
Okay, thank you so much.
Thanks.